Welcome back. So far we've just looked at how we're going to train our model. Now let's think about how we're going to use our persisted model to make predictions. So this brings us to our predict.py file. If we open this up, we have a few familiar bits of code here. So here's the version that we're going to come to very soon. And we have our config and some of our helper functions like this load pipeline that we've seen before in previous lectures. Now, we also have this validate inputs function, which we're going to look at in a moment. And then what we do is we specify the file name of the persisted pipeline, the persisted model that we're going to load. And this is all specified from a combination of config and version. And then we use our load pipeline function to initialize this price pipe variable. Then in our make prediction function, we take input data as the argument for this function, and we convert it to a pandas data frame. We apply bits of validation that we're about to look at, and the validate inputs function returns a tuple with validated data and errors that we can then put into a dictionary so that we can inspect that later on. There's one final transformation we apply to the predictions, so we calculate the exponential of all elements in the input array, and then we return these results. So this make prediction function is something that we'd expect to be able to import in our consuming application, and we're going to be looking at that in the next section. Let's dig deeper now into our validate inputs function, which lives here in the processing directory in the validation module. So we have a couple of functions here, and then a very large input schema. So this goes down quite a few lines, and then at the bottom here we have a wrapper around the main input schema. So in validate inputs we go through a series of steps. We go through the renaming process. You'll recall that we can't have a Python variable beginning with a number. We convert the type of the MS subclass column. Next we select just the columns that we're interested in, so our feature columns, and copy the data frame to this relevant data variable. And then our last step to create our validated data variable is to drop NA inputs in the relevant data frame. So this makes use of our drop NA inputs function, and we have here quite a complex list comprehension to generate our new vars with NA variable. What we're doing in here is iterating over the model config features, and so long as the features is not in this concatenated list, then we check for null values and we can drop those rows. This syntax here is concatenating lists. Each of these model config variables is a list, so categorical vars with NA frequent, a list, with NA missing, another list, numerical vars with NA, another list. So these are those columns where we're allowing NA values, but for the rest we drop them using the pandas drop NA method. So this is our sort of initial validation, and then the main event, as it were, is using our schema. This schema is another Pydantic schema, so we have the same base model approach that we did with our config, here imported from Pydantic. So once again we're making use of Python type hints to define all these different fields and what we expect their type to be. You'll notice that right now this schema is quite flexible in that all of these values are optional. If we wanted to be stricter, we could remove the optional, and then if we tried to run the validation process and one of these columns was missing, then we'd get a validation error from Pydantic. So on this line we have the multiple house data inputs, because there's obviously more than one. We've got many rows coming in here. This is a wrapper which has one field called inputs, which is a list of individual house data input schemas. So this represents a single data entry. And so we pass to the inputs the pandas data frame. We run this replace on numpy nan values. We replace them with Python none. That's so that Pydantic can understand what it's getting passed. And then we use the pandas to dict method to just take our data frame, convert it to keyword arguments that the multiple house data inputs expects. If instantiating our multiple house data input schema fails, then we will catch that validation error and update our errors variable, and then we're going to return a tuple of both the validated data and errors if they're applicable. So this is how we use our make prediction function. Now let's think about how we would test this to see it in action. So by way of exercise, I want you to pause the video and have a go at writing a test for this make prediction function, and then when you come back you can compare what you've come up with to the example we've prepared. Welcome back. Let's have a look at our test prediction file. Let me walk you through this one. So we have some sample data input, which again is using our sample input data fixture from ConfTest, same as we had when we looked at the test features tests. And then we have a little bit of setup here, specifying the expected prediction value for the first row from this sample input data, as well as the total expected number of predictions. We then pass this sample input data to our make prediction function, and then we get a whole load of results, and you'll recall that those results are a dictionary, so we're just grabbing the predictions key from that dictionary, assigning it to a variable, and then checking that it's a list and that the first value in that list is a numpy float 64, that we don't have errors, and that our expected number of predictions conforms to what we specified in our setup, and the same for our expected first prediction value. Here we're using the Python standard library math module and the isClose method from there, which checks that two values, so this is the first row and this is our expected value, are within an acceptable tolerance level, which we specify with this absolute tolerance argument. Let's test this out. If we go to our command prompt and we run tox-e test package, so we've got two tests passing. Now let's test. So if we specified, let's say 113,500 and run our tests, we'd expect this to still pass. Yes, that's within our acceptable range. But if we were to increase it by more than that, let's say to 114,000, and then run our tests, now we've got a failure because our maximum acceptable difference is 100 and we've gone up now by more than that. So this is illustrative. Again, in your tests you would have more tests than this, and you'd do things like testing the validation, any areas which could introduce bugs to your model you'd want to have tested. It's also good practice to check more than just a single row. You'd want to have the whole data frame or a subset of your test data being checked. And for your absolute tolerance, you would be as specific or as flexible as you felt you needed to be, depending on how big an update you'd made to your model, how deterministic the model is, what your risk tolerance is around these changes. Okay, now that we've had a look at making predictions, in the next lecture we're going to look at versioning and packaging.